Hello everyone! Welcome to another session in our Civil Engineering Review and Refresher. And for this video, we will continue our topics in dynamics and physics. So the featured topic for this video are the Newton's second law of motion and D'Alembert's principle. Newton's second law of motion states that the acceleration of any moving body is directly proportional to the net force acting on it and inversely proportional to the mass of the body. Okay? So, if the body is acted by a force system and the force system has a resultant force, meaning not zero, no? So the force system acting on the body or the body is not in equilibrium. So the body will move with an acceleration. And for example, if we have a car and then we have a force P acting na, then possible we have the friction force acting also opposite to the motion. So, between P and the friction, we have the net force. So, this car will move to the right with acceleration. So, Newton's second law states that the acceleration A is directly proportional to the net force and inversely proportional to the mass. So, we have here, acceleration is equal to the resultant or the net force over the mass of the body. Or we can write the net force is equal to the mass of the body times the acceleration. So we have here the notations used. So F net is the net force, M mass of the body, A as the acceleration, P any external force applied. There may be many applied forces, and F is the friction or any resistance force acting on the body. Okay. So, D'Alembert's principle says that, or this is an alternative form of Newton's second law of motion. Actually, D'Alembert's principle and Newton's second law are just the same. Only that, in D'Alembert's principle, this says that static condition can be obtained by an accelerated body by the addition of the reverse effective force. And the reverse effective force is equal to the mass of the body times the acceleration, and that is directed opposite to the acceleration. So let us say we have here a body, so let us say we have a car, and then we have the net force, the resultant force acting. So this will move with an acceleration. Okay. So if this moves with an acceleration, of course, we cannot apply our static equation for the body. So we need to make this in equilibrium. So this will be in equilibrium by the addition of the reverse effective force. And the reverse effective force is equal to the mass of the body times the acceleration and directed opposite to the acceleration. Also, we have a moving car. And then, let us say this is moving with constant velocity, so there is no acceleration. Then, let us say the motion is to the right. Then, there is a resisting force acting. So let us say we have a resisting force in this. Let us say the car or the driver of the car applies a brake. So if we have the net force acting opposite to the motion, so this will be decelerated. So decelerated, and so we have the reverse effective force acting opposite to the acceleration. So as you notice, this is the explanation in this situation in which if you are riding a car, for example, in the first illustration here, if you are riding a car and then the car will accelerate forward, so what have you experienced is that as if you will be or you will be pushed to the opposite direction of the motion. So you will be pushed to the back of your seat, no? That is the action of the reverse effective force. Then in the second illustration here, let us say the car where you are riding on a car, no? So if you are riding on a car and then the car or the driver applies the brake, so this will decelerate. So the reverse effective force is the action wherein you will be pushed forward. So the driver applies the brake and then you are riding here in the car. So you experience a pushing forward. And that is the action of the reverse effective force. So by the addition of the reverse effective force to the moving body, where the body is moving with acceleration, you can now apply our static equation. So in this situation here, we can now sum up forces along x equal to 0, and we have the net force equal to the reverse effective force. Then substituting the reverse effective force equal to the mass times acceleration. So as you notice, still we have the Newton's second law equation. So that is the difference between the Lambert's principle and the Newton's second law. So they are just the same. When you apply the equation, the resulting equation are just the same, only that in the Lambert's principle, you have the addition of the reverse effective force, which is the force you experience when you will be moving with acceleration, and then when you move with an acceleration, then you experience the reverse effective force. Problem number 1, a horizontal force of 5,000 Newton is applied to a car at rest whose weight is 10,000 Newtons. What will be the car's speed after 10 seconds? Okay, so at first, we will analyze the forces acting on the car. So this is the car. We have the weight 10,000 Newton, and then this has an applied force of 5,000 newtons. So let us say the 5,000 newtons is applied to the right, so this will move to the right direction. Then we have the acceleration. So we have the weight 10,000 newton. So in this case, the car will accelerate. And by Newton's second law, this net force, wala namang ibang force na nag-act dito, So the net force is simply equal to the 5,000 Newton, and that is equal to the mass times acceleration. But the mass of the body is equal to weight over g. So 5,000 equal to 10,000 over g times a. So we can solve for the acceleration 4.905 meter per second squared. Then, if we analyze the motion, the car is at rest. At first, the car is at rest, so meaning initial velocity is 0. Then, what is the speed after 10 seconds? So we can use final velocity equal to initial plus acceleration times time. So final, V1, the initial is 0. So we have V equal to acceleration, which we have computed, times 10. So velocity is 49.05 meters per second. Okay, how about if we will use the Lambert's principle in solving this problem? So same figure, we have the net force, the 5,000 Newton, and since this will accelerate to the right, then we add the reverse effective force opposite to the acceleration, equal to mass times acceleration. So, summation of forces equal to 0. Summation of forces along x, Okay, so REF equal to 5,000. But REF is mass times acceleration. So, we have this. So, acceleration is equal to 4.905 meter per second squared. Then, we have this equation for the motion of the car. Then, V1 is 0. We can solve for the final velocity, 49.05 meter per second. Okay, so in the succeeding examples, you can use either Newton's second law or you can use the Lambert's principle. Na? Okay, so we have the next problem here. A crane is lifting a pallet on which stone blocks rest, each of mass 5 kilograms. So each stone block weighs or has a mass of 5 kilograms. The crane lifts the pallet vertically upwards from rest to a speed of 3 meters per second in a height of 6 meters. When the contact force between the pallet, I think wala tong on na. I'll just erase this. Okay. So, when the contact force between the pallet and the stone blocks exceeds 650 newtons, the pallet may break and the situation is considered unsafe. So, question, how many stone blocks can the crane lift safely? So, let's say we have here a pallet. So, I will use first this Newton's second law. So, we have the pallet and then we have the stone blocks resting on it. Then, the crane lift this. So, starting from rest, so meaning initial velocity is 0, the speed to a speed, so final velocity of 3 meters per second, and the height traveled is 6 meters. So, we have the weight, W. Then, we have the normal. Okay. So, the normal N is the normal contact force between the pallet and the blocks. Okay. So, since this is accelerated upward, we can solve for the acceleration based on the given information of the motion upward of the pallet. So, we can have V equal to 0 or V1 initial 0, final is 3, height is 6. So, V squared equal to V1 squared plus 2AH. So, V1 is 0. So, 3 squared equal to 2A times 6. So, acceleration is 0.75 meters per second squared. Okay. Then, since this moves with acceleration, so meaning, the net force, so the net force here is the difference between the weight and the normal. So, the net force is the difference between the weight and the normal. So, F net is upward. So, our F net is equal to N minus W. So, F net is equal to N minus W. Then, our F net is equal to mass times acceleration. And our N is 650 newtons. So, we have here, MA equals 650 times mg. So, the weight is now equal to mass times g. So, we have acceleration, we have g. So, we can solve for the mass, 61.55 kilograms. So, meaning, when you apply a net force in order for this to accelerate upward, the net force is such that the mass of the stone blocks placed on the pallet should not exceed 61.55 kilograms in order for the pallet to be safe. Then, each stone block weighs or has a mass of 5 kilograms. So, we can now compute for the number of blocks. So, M equal to 5N. So, where N is the number of blocks. So, 12.3. So, the maximum number of blocks that can be carried by the pallet is equal to 12. Okay, so this is Newton's second law. Now, how about if we will use our D'Alembert's principle? Okay, so still we have the same figure. And since this is accelerated upward, we apply the reverse effective force downward. Mass times acceleration. So the same motion, so the acceleration is still 0.75. And then by the addition of the reverse effective force to the system, we can now apply our static equation. So if we sum up forces vertical equal to 0, so downward is REF plus W equal to N. So N upward equal to W plus REF. So N is limited to 650 newtons. Weight is the unknown. REF is mass times acceleration. So 650, weight is m times g. REF is mass times acceleration. Then we can solve for our m. So we have m equal to 5n. So we can solve for n, that is equal to 12 blocks. So the same lang, no? The only difference is that when you apply the reverse effective force, you can apply the static equations. Pero pag gamitin mo yung Newton's second law, tingnan mo kung saan ang acceleration. So pag ang acceleration upwards, of course, upward forces minus downward forces, that is the net force. So the forces in the same direction as the acceleration are positive. Opposite direction to the acceleration are negative forces. Okay? Next problem we have here. A driver sees a roadblock ahead and applies the brakes so that the car stops in 24 meters. The road is level and the coefficient of kinetic friction between tires and road is 0.6. How fast was the car going when the brakes were applied? Okay? So we have here the car, and then the driver sees a roadblock ahead and applies the brake, and the car stops in 24 meters. So the coefficient of friction, so there is a friction force na between tires and road is 0.6. So how fast was the car going when the brakes were applied? So the question here is the initial velocity of the car when the brakes are applied. Now, the final velocity is 0 because the car stops. And the distance S traveled is 24 meters. Okay. We will solve first for the acceleration. Okay. So, the car is moving, and then when the brakes are applied, we have the friction between the tires and the road that makes it stop. So we have the weight, and when we have the normal force. So if we use second law of motion, so this is decelerated. So decelerated. So motion to the right, but the acceleration is to the left. Okay? So our net force is equal to the mass times acceleration. There is no other force acting, no? Only the friction when the brakes are applied. So we have our F net equal to mass times acceleration. So F net equal to mass times acceleration, and that is equal to mu times n. So F net, mass times acceleration, equal to the friction coefficient times the normal. But the normal is equal to the weight. So mass is W over G times A. So W cancels out. So our acceleration is equal to U times G. Coefficient of friction 0.6, G 981. So acceleration is equal to this. So this is negative acceleration, deceleration. So initial velocity is unknown. Final is 0. Distance is 24. Find V1. Using this formula. Convert to kilometers per hour. Problem 4, we have here. A wedge has two smooth sloping faces. One face makes an angle of 30 degrees with the horizontal, and the other makes an angle of 60 degrees with the horizontal. A smooth pulley is fixed at the apex of the wedge. A light inextensible string passes over the pulley and lies parallel to the faces of the wedge. At each end of the string, there is a mass of 0.3 kilograms. The system is then released from rest. Compute the tension of the string and the acceleration of each mass. Okay. So, in math, most problems are worded, no figure given, no? So, if the problem is worded, then we have to draw the figure correctly, no? So, there is a wedge with has two smooth sloping faces. One face angle of 30 with the horizontal, the other angle 60 with the horizontal. So, this is the wedge, no? At the apex, meaning at the vertex, na, there is a smooth pulley. Then, a light inextensible string passes over the pulley. And the other lies parallel to the faces. Yan. Then, at each end, we have the masses of 0.3 kilogram each attached. So, at first, this is being keep at rest. Then, the system is released. Compute the tension of the string and the acceleration of each mass. Okay. So, if you try to check, so, I will call this mass A, mass B. So, the weight of each is 0.3 kilograms times 981, so 2.943. So, we have here 2.943. So, if you take the component of this, parallel to the incline, so, siguro, we are familiar this already, no? The normal is the weight times the cosine of this angle. While this component along the incline is the weight times the sine of the angle. So, we have here 2.943 sine of 30, that is 1.47. We have here also the component 2.943 sine of 60, that is 2.55. So, if we try to check, if we just consider the system as at rest, this is 1.47, this is 2.55. So, meaning, when released from rest, this will move to the right. Block A will move up, while block B will move down. With an acceleration, of course. From rest, and then with acceleration, this will move up. Okay. So, the motion is to the right. We note that. Okay. So, consider A. So, this is mass A. Then, we have the force here, the tension. No need of having the normal because there is no friction mentioned here. Okay. So, this is accelerating upward by A. So, meaning, since this moves upward with acceleration, the tension here is not equal to 1.47. Not equal to 1.47. Pero, pag walang acceleration, or that is at rest, so of course, T is 1.47. So, why? Because, if you try to analyze, if you apply the Lambert's principle, since this will move upward, then there is a reverse effective force acting opposite to the acceleration. So, the tension here is equal to 1.47 plus the reverse effective force. Okay? But, if we solve this by Newton's second law, we can just say that T is greater than 1.47. And the difference between T and 1.47 is equal to mass times acceleration. T minus 1.47 equal to mass times acceleration. Then mass is 0.3. So I will call this equation 1. Consider block B. We have the component 2.55 of the weight. Then we have the tension T. The same tension, no normal because no friction mentioned there. Then, this is accelerated downward. So, meaning, if we apply Newton's second law, 2.55 is greater than t. And the difference between 2.55 minus t is the net force, and that is equal to mass times acceleration. Then mass is 0.3. I will call this equation 2. Then we solve equation 1 and equation 2 by adding, no? So if we add 1 and 2, t will cancels out. So negative 1.47, 2.55, we have a difference, and then 0.3, sum, no? 0.3 plus 0.3 is 0.6. So we have t cancels out. Negative 1.47 plus 2.55 is 1.08, equal to 0.6 of a. So we can solve for the acceleration 1.8. And then we can substitute to either equation 1 or 2, no? To 1. So when a is 1.8, we can solve for the tension in the string. Okay lang? Again, if you use D'Alembert's principle, this is accelerated downward, so we have the reverse effective force, opposite to the acceleration. And then, if you try to check the summation of forces along this incline, the equation form is just the same to this. Kaya, I just use the Newton's second law. Last problem we have here. For the figure D-101 shown, block A is 400 newtons, block B is 680 newtons, coefficient of friction 0.2. So of course this is between the inclined and block A. Compute the following. Okay. So number 1, acceleration of the 400 newton block. Tension on the cord supporting the 400 newton block. Tension on the cord supporting the 680 newton block. Okay. So, I can consider block A na. So, consider block A. This is the weight, 400. Then this is 20 cosine, 400 cosine 20. Is it 20 degrees? Try to check. 20 degrees na. Okay. So, we have here 400 cosine 20. Then, we have here 400 sine 20. We have the normal, We have the normal force. And then, we have the tension of the string holding the block A. Then, normal is just equal to this component of the weight, so, this is accelerated upward. So, meaning the friction is opposite. Okay? So, this is 0.2. 375.88. This is 75.18. Okay. So, since this is accelerated upward, I will place the acceleration, this will accelerate up because this component of the weight is very much lesser compared to the second block, 680 newtons. This is only 136.81 pulled by 680 newtons. Okay. So, since this is accelerated upward, meaning the tension is greater compared to the sum of the friction and this component of the weight. That is why this moves up. So, by Newton's second law, P1 minus F minus... dito pala yung acceleration. Akala ko wala, i-erase na lang natin tong isa, Yan. Okay. So, as you notice, if you sum up, or if we take the net force is the difference T1 minus F minus 136.81. And that is equal to the mass of A times the acceleration. So we can sum this up, then 400 over G for the mass. Call this equation 1. Then I can consider block B. So notice that the string holding B Now, we have here the weight 680, tension T2, and this is accelerated downward. But take note, the string is being looped to another pulley here. So, the acceleration or the motion of B is just half as the motion of A. So, if A is accelerated by small letter A na acceleration, B is just accelerated A over 2. Then, we can apply the Newton's second law. So, of course, this is accelerated downward. So, 680 is greater than T2. So, the difference, 680 minus T2, is equal to mass times acceleration. But take note, the acceleration of block B is only A over 2. Na? So, 680 minus T2 equal to 680 over G times A over 2. Then, we have the result here. Na? But, if you consider the pulley, this pulley, so if the tension of block B is T2, then we have the tension here is T1. This is also T1 here. So we can say T2 is equal to twice of T1. Then I will call this equation 3. So I can substitute it here. So 680 minus 2 T2 equal to 34.66 of A. So I have equation 1 for T1. I can substitute it to equation number 2. No? So we have here T1 is equal to this. So from this, the only unknown is the acceleration A. So that is 2.2, the acceleration of block A. Then substitute 1 with acceleration equal to 2.2. We can solve for T1 equal to 301.16. Then since T2 is twice of T1, so T2 is equal to 603.36. Okay, so this is about Newton's second law of motion and D'Alembert's principle. So thank you very much for viewing my video. I hope my discussion helped you in your studies. Then stay tuned for the next videos to come.